Well, it's exciting to see so many people in our community and Division of Chemical Physics coming together, and we thought this would be just a great forum to highlight the relevancy of chemical physics across many disciplines. As we know, chemical physics underlies many chemical and physical processes, and having a forum that we can have these talks to highlight those emerging stars and those established leaders in the field. And yeah, and really just get to hear some really good science. I'm excited for this series here, and that's all I'll say. I'll leave it up to Zeke. Take it away.
Yeah, so we have two exciting talks today, and I'm really excited to introduce our first speaker, which is Professor Camille Bilodeau from the University of Virginia. She's an assistant professor of chemical engineering. Um, Before joining Virginia, she did her PhD at RPI with Shekhar Garde and Stevie Kramer. And then followed that with a postdoc at MIT with Klaus Jensen and Regina Barzilai. Camille's gotten a large number of awards in her scientific career. Most recently, she's a recipient of the SF Career Award, and she's been heavily involved in leadership within the scientific community. And today she's going to be telling us about how this charge impacts surface hydrophobicity. And go ahead, Camille, you can share your slides and you're muted, Camille.
Sorry about that. Thank you so much for that introduction, and thank you so much for the invitation to be here today. I'm really excited to share my work. So, as Zeke mentioned, I'm an assistant professor at the University of Virginia. I've been here for a few years now, and so this was one of kind of the first projects that we started, really asking this fundamental question: how does charge impact hydrophobicity? Which is really one that has been nagging at me really since I was a first or second year PhD student. Before I get into the details of this, I want to start off by just thanking my students. So in particular, Jakir, who is a rising third year, is really the person who did a lot of this work. And so I want to thank him as well as, funding and all of that fun stuff. Um, okay. And so the question we're asking here is, how does charge impact hydrophobicity? And so while this might seem like an academic question, the reality is that surfaces containing hydrophobicity and charge are really all over the place in nature and engineered materials. And so, for example, biological membranes often incorporate lipids with charged head groups, along with fatty acid tails. Separation materials like desalination membranes are often comprised of hydrophobic polymers that have been functionalized to introduce charge groups that can selectively interact with ions. And then catalytic materials, such as things that include nanoparticles, often contain combinations of charge and hydrophobicity at their interfaces in order to catalyze reactions selectively. And so what we really want to ask is this core fundamental question: well, how does water interact differently when it's interacting with a surface that is characterized by a combination of hydrophobic and charged kind of physical moieties? And so, of course, we're not the first people to ask questions in this area. And so I want to start by just giving you a snapshot of some of the key things that we already know about these mixed charge hydrophobic surfaces. And so first, there have been a number of experimental studies aimed at really unraveling the impact of charge on hydrophobicity. And in particular, Nick Abbott's group at Cornell performed a series of interesting experiments where they functionalized the tip of an AFM probe with a hydrophobic methyl SAM surface, and then they measured how strongly this probe interacted with two types of surfaces that are hydrophobic and charged. One, a mixed methyl ammonium surface, and one, a mixed methyl guanidinium surface. And so by measuring the interaction strength between these two surfaces in water and water methanol mixtures, they were able to back out the strength of the hydrophobic effect for these two surfaces. And overall, what they found was that the ammonium surface was significantly more hydrophobic than the guanidinium surface, despite the fact that both of these surfaces are essentially just hydrophobic and positively charged surfaces. And so, in other words, the exact nature of the charge group chemistry has this significant impact on hydrophobicity. And so this is cool. But one of the other things we're interested in understanding is, well, what about the patterning and spacing of the charge groups on the surface? And so a number of studies have shown that the actual exact arrangement of uncharged hydrophilic and hydrophobic groups can play a major role in determining surface hydrophobicity. And as an example, this study out of Reed Van Lane's group at Wisconsin recently showed that if you compare a mixed hydrophobic hydrophilic surface with a surface where we've completely separated the hydrophilic and the hydrophobic groups, you'll find that the separated hydrophilic groups results in a more hydrophilic surface compared with a kind of segmented surface containing hydrophobic groups to one side and hydrophilic groups to the other side. And this result is generally consistent with a lot of previous simulation studies, which really show broadly that more even spacing of hydrophilic groups tends to lead to a more hydrophilic surface compared with distinct kind of separated patches or clusters. And so from these previous studies, we really have this expectation that the exact type of charge group chemistry and their spacing or arrangement on the surface should play this significant role in governing how the overall surface hydrophobicity should behave. And so the overall question we want to ask is, well, how does charge group chemistry and arrangement impact the overall hydrophobicity of these charged hydrophobic surfaces? And why, right? What is the underlying molecular mechanism behind these effects? And so to probe this question, what we've done is we've basically performed classical molecular dynamics simulations where we construct a self-assembled monolayer at the base of our simulations. We set this up so that the strands are at a twist and a tilt that is associated with being immobilized at a gold 111 surface, but we don't actually represent the gold itself. Here we just have this surface, and then we have this kind of tall box containing all of this water, and we're basically going to study what's going on at the interface between the self-assembled monolayer and the water. And so then to study this question, we're going to study a series of different spacings from low to high spacing, basically just spacing out hydrophilic or charged groups out by increasing numbers of hydrophobic groups. And so here, we're going to start by looking at two kind of control groups, one a fully methyl surface, which is kind of our control hydrophobic surface, another fully hydroxyl surface, which is sort of our control hydrophilic surface. And then we're going to study a series of methyl surfaces with these hydrophilic groups placed at increasing spacings. And so starting with a hydroxyl group, then studying a charged amine group, and then studying a positively charged guanidinium group. But before we get into kind of the details of how to analyze hydrophobicity, we have to start by really agreeing on what hydrophobicity actually is. And so this is actually something that is somewhat kind of debated in the literature. There's a lot of views on what hydrophobicity fundamentally is. And so we'll think of hydrophobicity kind of at a high level is this tendency of nonpolar molecules to be effectively attracted to one another, because in water, they're trying to avoid disrupting water's hydrogen bonding network. And so the way that we think about this is, if I want to think about the overall binding process of a solute binding to a surface, we can think about this as this kind of delta G of binding process, right? Where we have this one system where the solute is in the bulk, solute is at the interface, and we're looking at the delta G of this process. But if we want to specifically isolate the effect of the impact of rearrangements of water structure on this, we might be interested in instead in first thinking about what is the free energy of removing water molecules in order to make room for that solute. And so then what is the free energy associated with creating this cavity, as well as then inserting the solute into this cavity. But then if we want to actually connect this back to this binding free energy, what we really need to do is define a fourth scenario. What about the free energy of forming a cavity at this interface? And so we can think of sort of as the hydrophobic contribution to this binding free energy is really the change in the free energy of binding associated with the difference in free energy between forming a cavity in the bulk and forming the equivalently sized cavity at the interface. And so we can then think about this process in terms of binding as proceeding through forming the cavity in bulk, forming the cavity at the interface, and then introducing this, basically inserting our solute here. And so we can kind of think about the overall free energy of binding through either of these kinds of angles. And if we want to really focus in on a solute independent definition of hydrophobicity, we really need to be thinking about, this cavity formation process, right? What is the free energy associated with forming the cavity in bulk? And how is this different, or how does this change if we instead form this cavity at the surface? Because this will be kind of thermodynamically a major contributing factor to the overall free energy of binding. And so this is a way that we can think about hydrophobicity in a manner that is a bit less dependent on the solute itself. I'll say mostly for now, and we can come back to that later. We can also think about the other half of this as maybe being a more solute-dependent hydrophobicity. And so if we have different kinds of idealized hydrophobic probes, we can maybe measure the hydrophobicity of a surface by just measuring the free energy of that hydrophobic probe binding to the surface. And so the way that we think about this in my group is the kind of left-hand side of this is the true, pure definition of hydrophobicity. But the right-hand side of this is also important because when we think about these practical applications like separation materials, adsorption and catalysis, we often do care about real hydrophobic molecules binding to surfaces. And so it's worth thinking about comparing and contrasting these views. Okay, so how do we measure first this solute agnostic definition of hydrophobicity? And so here, our key insight is that this difference in the free energy of forming a cavity in bulk versus forming a free energy or cavity near the surface is really going to be dominated by the free energy associated with removing water molecules. And so to probe this, we can use an enhanced sampling technique called indirect umbrella sampling. And this looks something like this. I like to show this little syringe because effectively what we're doing is we're placing a cavity near the surface, we're introducing a biasing potential, and we're trying to push water molecules out of this cavity. And what we can do is we can then measure the number of water molecules in this cavity as a function of this potential. So you can think about this as a syringe. We're kind of systematically pulling water molecules out of this cavity. And so we get a curve that looks something like this. Typically, we can think about this curve as broken down into a few different regimes. First, the linear response regime, and this is really where we're just enhancing our Gaussian fluctuations. And so in general, this is always going to have a linear shape, but the slope of this can be different for different surfaces. Then after this, we see this kind of stark drop, and this is associated with a cavity nucleation process. And so here we've basically formed a cavity, kind of undergone a phase transition, and now we're growing that cavity. And then depending on the nature of the surface, we may have a third phase, which I call hard to remove waters. And so depending on the surface, we may not have this, but this is where we maybe see a slow tail at the end. And so to illustrate what this looks like for our surfaces, we can start by looking at the methyl surfaces and the hydroxyl surfaces. And overall, what you see is these three distinct phases, but just to point out a few interesting features, we see that depending on the chemistry surface of the surface, we get somewhat different slopes. And in particular, we see a steeper slope for the the methyl surface, the methyl/hydroxyl surfaces, and then we see a shallower slope for the hydroxyl surface. And this is consistent with previous literature results. And so this kind of illustrates that you can think about this compressibility as maybe being related to the hydrophobicity of these surfaces, which has been studied pretty extensively. Then you can also see that we experience these different points of cavity nucleation. And so, but the cavity nucleation process is very steep for all of these surfaces. And then finally, at some value of beta phi, which again is this potential pulling water molecules out, we see that we effectively have removed all of the water molecules. And so we see kind of rapid cavity nucleation and no difficult to remove water molecules. So when we tried to apply this kind of thinking then to charged surfaces, we saw some interesting differences. First, when we look at the guanidinium and ammonium surfaces, what we see is we actually see very similar initial slopes, meaning that the compressibility of the first water shell near the interface is very, very similar. And it actually, if we were to overlap this with our previous surfaces, it's similar to the methyl surface. And so it seems like the methyl background really dominates the overall compressibility. We also see that the cavity is nucleated at a somewhat similar point for all of our surfaces. And then where the real differences in the free energy of dewetting come from are the growth of this cavity, as well as the difficulty associated with removing these final water molecules. And so really the overall kind of process associated with dewetting this surface is fundamentally a little bit different than near these more simple surfaces that are uncharged, because the growth process is a bit less steep. It's kind of challenging because these cavities are trying to grow around these hydrophilic charged pins. And so we don't necessarily see this kind of first order phase transition type behavior. From this, we can use a thermodynamic integration type of approach to actually quantify the free energy of removing these water molecules. And so because we aren't able to remove all of the water molecules from all simulations, we quantify the free energy of removing most of the water molecules up to beta phi equal to 7. And what we get is something that looks like this. So I'll start by just showing you the free energy of removing water molecules near the methyl versus the hydroxyl surface. And the first thing I'd like to point out is that, the free energies are all unfavorable because, of course, the water doesn't want to be removed from any of these surfaces, but it is much easier to remove water from the methyl surface compared with the fully hydroxyl surface. So these are our homogeneous surfaces. We can then look at the ammonium, hydroxyl, and guanidinium surfaces in this S0 configuration, meaning that the hydrophilic groups are all kind of clustered toward the center of the indus cavity. And then what we find is that the hydroxyl surface gets slightly more hydrophilic compared to just the methyl surface alone, but then the ammonium and guanidinium surfaces are far more hydrophilic than the hydroxyl surface, which is maybe to be expected, right? These are both charged, and so they're interacting much more strongly with water. And then the other thing to note is that they're quite similar. They're within error of each other. When we then space these charged groups out a little bit further, what we find is that the free energy of dewetting these surfaces actually goes up quite a lot. And so even though the backdrop is all methyl surfaces, or is all methyl groups, and so the compressibility of this, the first water shell near this surface is quite similar to the methyl surface, the free energy of removing these water molecules is actually much more similar to the hydroxyl surface. So these are very hydrophilic surfaces. And so compared to our initial hypotheses, we found that the increased spacing between hydrophilic charged groups leads to increased hydrophilicity. And so this was really consistent with previous simulation results, which had shown this for like hydroxyl methyl groups and uncharged surfaces. And so we're seeing that indeed, as we expected, this is also the case for charged surfaces. But we also found that the mixed methyl ammonium surface was somewhat indistinguishable from the mixed methyl guanidinium surface. The overall free energy of dewetting these surfaces was really similar. And so we saw that this was a little bit different from those previous experiments. And so to try to understand a little bit more about what was going on with these surfaces, we looked at the dewetted area near the surface for each of these systems at a beta phi equal to 7. And so here in black, I'm showing high water density, and in white, I'm showing low water density. So you can think of black as basically being water molecules that we've failed to actually remove. And so what you can see in particular is that ammonium is really holding onto water molecules. And so you can see these stark kind of black regions around ammonium. However, guanidinium is not holding onto water molecules as much. Although despite the fact that there's a little bit of a difference, maybe just a subtle difference in terms of these dewetted areas, it appears that this doesn't necessarily lead to a substantial difference in the overall free energy of binding. So with that, we were trying to understand why might we see this difference in where we see the mixed methyl ammonium surface being similar to mixed methyl guanidinium surface in our simulations, but this is inconsistent with experiments. And so to try to understand the discrepancy between the simulations and experiments, we decided to try to cook up a simulation protocol that might be a little bit more similar to those experiments. And so we started thinking about solute-dependent hydrophobicity. And what we came up with was we decided to do kind of standard spatial umbrella sampling with a gold nanoparticle that was functionalized with a methyl SAM surface and perform umbrella sampling with our surfaces. And so this we think is very similar to kind of that AFM tip. And so again, if we look at the free energy of binding, now all of our free energies of binding will be favorable. So we kind of have to change our frame of reference. We see that we get a very favorable binding of this gold nanoparticle to our methyl surface and, slightly favorable binding to our hydroxyl surface. If we look at this closest separation, you can see that we get a slightly less favorable binding when we introduce the hydroxyl groups. But when we introduce ammonium, this becomes a lot less favorable. And when we introduce guanidinium to the surface, we actually see no minimum. When we then space out our groups a little bit more, we see a further decrease in the overall free energy of binding. And in particular, we see no minimum for either guanidinium or ammonium. And then as we continue to space out our groups, we now start to see where the nanoparticle is able to fit somewhat between these groups. And so we still see stronger binding to ammonium compared to guanidinium, but now they're a bit more favorable. And then finally in the S3 configuration, we see that the binding has become quite a lot more strong, and we see a little bit of an order reversal. And so overall, the trends I want to point out here are that now we do see that ammonium is actually significantly stronger bound than guanidinium. And so now we do see a difference in the binding between ammonium and guanidinium. And we also see that we observe that the S1 configuration sort of maximizes surface hydrophilicity for this specific solute. And so that's kind of what I'm writing down here. And so to try to understand where this difference might come from, we decided again to turn to kind of these de-wetted areas. And so overall, what we found is that while obviously with the Indus simulations, we're really removing most of the water molecules within that kind of area around the hydrophilic groups, as you might expect, in many of these configurations, the gold nanoparticle doesn't actually form all of the contacts it can. And so in many cases, it actually kind of shifts about when it's binding to these charged ammonium and guanidinium surfaces. So for example, if we look at this guanidinium in the S0 configuration, because the gold nanoparticle doesn't want to bind over these guanidinium groups, it actually just prefers to find a little bit of a binding interface slightly outside and just forms more of a partial contact. And so really what we're seeing is that we're not de-wetting the whole surface, we're de-wetting a part of the surface that is more favorable. And then overall, we also see that this de-wetted free energy is actually really strongly correlated with the delta G, or the free energy associated with binding. And so we think that what's really happening here is that what's governing the differences in free energy of binding is that this is really coming from differences in the kind of footprint that the gold nanoparticle is able to find on the surface. And so overall, the conclusions here were that we found that we saw an optimum hydrophilic group spacing that results in minimized hydrophobicity for ammonium and guanidinium, at least for the context of our gold nanoparticle. So it remains to be seen how this might be affected if we instead looked at a larger length scale solute, or even a smaller length scale solute. And we also found that the relative hydrophobicity of these different interfaces really depends on your point of view. So if we're coming from the perspective of trying to understand how a methyl SAM surface binds to the surface, we did see that this ammonium methyl surface gives us a more kind of hydrophobic interaction or stronger adsorption. However, if we instead focus on the energetics of de-wetting, so what is the free energy of forming that cavity, we found that ammonium methyl and guanidinium methyl surfaces have similar energetics of de-wetting. And so the places that we want to go with this now are First, we're interested in exploring chemical space and really trying to understand how other charge groups impact surface hydrophobicity beyond just methyl ammonium and guanidinium surfaces. We're also interested in taking this past just these patterned SAM surfaces and thinking about how does this look for ligand functionalized surfaces where now maybe the groups can actually move around and interact with one another. And then finally, we're interested in bringing this to protein surfaces and trying to understand how different protein motifs can lead to different kinds of hydrophobicity. And so with that, I'd just like to thank you all for your attention. And again, thank my group. And in particular, like I said, Jakir is really the student who has kind of led the way on this project. And I'll take any questions.
Yeah, thank you, Camille, for your talk, and we have some time for questions. So if you have questions, you can either ask them in the chat or you can raise your hand. And since we already have a question in the chat, I'll go ahead and read that. So this question is from Matt Eager, and it's, is the three-phase response per unit area? How big is a cavity?
The three-phase response, is that like
I think that's in the Indus potential plots, but
like this part per
yeah.
unit area? Oh, that's a good question. I have not thought of that. So I guess I want to make sure I understand, like, all of these are operating on the same Indus overall area, and then all of the y-axes are normalized by number of water molecules. So that also kind of serves as some kind of normalization, but we don't explicitly normalize by area. But I don't know if there's a specific like thought process behind that question, like
So
what we expect the difference to be.
I see the equilateral triangle you've drawn there, which kind of bounds all of your, spaced out corners of the groups lying on the surface. So I'm wondering about how that equilateral triangle you've drawn relates to the size of the cavity or the total area that you're considering when you're figuring your free energy.
Yeah, so I guess to give you a better sense of what this actual cavity looks like, I drew it as a cartoon as an equilateral triangle, but the real cavity is the way that Indus works is we can define a cavity as being like the union of spheres around the heavy atoms that make up the SAM surface. And so the reason why we did it that way is because we wanted to kind of create a definition that would also work for more flexible surfaces, like surfaces that contain ligands and things like that, where you might see some kind of more complex topology. And so practically then we also didn't want to define a cavity that covered the whole surface, because if we do that, or even just a substantially bigger cavity than this S0 or S1 spacing, we end up getting kind of weaker signal. We don't see the impact of these hydrophilic or hydrophobic groups as much, because we're mostly looking at like the methyl surface. And so for that reason, we kind of tried to draw like it's not quite a triangle because it's a triangle made up of a union of spheres. You can see the edges are actually rounded. But so these would be roughly the same size. They end up being slightly different because, as I mentioned, they're union of spheres around the head groups. And so it is slightly larger for ammonium and guanidinium. And we did not necessarily normalize for that outside of the fact that here I am plotting this divided by the number of water molecules in the volume. And so in that sense, we're kind of scaling in the y-axis associated with, if the volume is bigger, we're kind of scaling down. And so then they all fall on top of each other for that reason.
It looks like we have another question from R.A. Rosenstein. You can unmute.
Oh, yeah. First of all, thank you for a very interesting talk. I was thinking about the mean force potentials you displayed. Are those, is that a, do you, is that a universal feature for all the systems, or are the qualitative features of that mean force potential system dependent? And secondly, I remembered decades ago reading some work by the late David Chandler on hydrophobicity of methane dissolved in water. I wonder if there's any connection of those earlier studies with this more innovative, up-to-date work.
Yeah, great question. So I'm not 100% sure if this is exactly what you're thinking of, but there's a length scale dependence here, which I know that's when I think of David Chandler and hydrophobicity, I think of length scale dependence. Um, and so basically, here we're really only studying this with one size gold nanoparticle. And I think, for example, we see that there's a sort of maximum at this S1 spacing. And I'm not sure to what extent that is a function of the exact size of the gold nanoparticle. I would expect that at some point we would see that the free energy of binding would go back down even for a larger solute, just because there is some evidence here, and there has been evidence elsewhere that there's sort of a cooperativity effect, where if you imagine you have hydrophilic groups, and they're kind of bonding, or they're hydrogen bonding to water molecules, that maybe those water molecules are also hydrogen bonded to each other. And so they can kind of create like a cooperative hydrophilicity, and that if they move further apart, they lose that cooperativity effect. But then I think here there's the confounding effect of eventually, if they're far enough apart, the gold nanoparticle can actually fit between the hydrophilic pins. And so we haven't like fully, I think, I had been hoping to probe that question, and then I found that question to be kind of difficult to decouple from just the idea of the solute fitting between the pins. And so I also think if you went even smaller, that you could get different results, just by virtue of here at the smaller distances, for example, again, the gold nanoparticle can't fit between the hydrophilic groups. And I've seen work recently from Rick Remsing's group, which suggested that at these kind of S1 and S2 configurations for different systems, not these charged groups, but where he actually saw that you get even more hydrophobicity if you have a small solute trying to sit in between these hydrophilic groups than if you just had it binding to a hydrophobic surface alone. So I think there's a large length scale dependence element to this, that I don't fully understand yet.
Okay, thank you very much.
Yeah, thank you. Thank you for great questions.
All right. Well, thank you again, Camille. Really enjoyed your talk, and I think Nathan is going to introduce our next speaker.
Perfect. Well, wonderful talk, Camille. Thank you so much. Our next exciting talk will be presented by George Schatz. George Schatz is the Charles E. and Emma H. Morrison Professor of Chemistry at Northwestern. Received his undergraduate degree at Clarkson University and PhD at Caltech. Postdoc at MIT, and has been at Northwestern since 1976. During George's elaborate career, he's of course a member of the National Academy of Sciences, American Academy of Sciences, received numerous awards, one that's near and dear to my heart, the Marshall Lester Awards of the ACS. Also a fellow of the APS, the Royal Society of Chemistry, and the ACS and the AAAS. George, the floor is yours.
Thank you very much. Pleasure to have a chance to speak to this group. Thanks to the audience. Thanks for coming to this. And thanks also to the Division of Chemical Physics of the APS. I was the chair of this division way back in the 1990s. Okay. And so, it's a very much grassroots organization. It's terrific to see that you've, developed this program. It's really nice to see what's happening. All right, so I'm going to talk about plasmons, okay, and I guess I should begin by just talking about, okay, what is a plasmon? Let's see. Oh, here we go. Okay, all right, so actually we start with something that's actually related to what Camille was just talking about, which has to do with the properties of colloidal gold. Okay, so if it turns out, if you take little 10 nanometer sized particles of gold, suspended in the water, and there are ligands and there's charge and everything. That's what Camille was talking about. Okay, but it turns out instead, if you just think about what's the color that you get out of this, okay, you get this characteristic red color, okay, of colloidal gold. And if you take the absorption spectrum of the of that, you discover that there's this big peak at 520 nanometers, which is in the green region of the spectrum. And so that's some sort of excitation that's occurring. And similar with silver, it's a yellow colored liquid, which corresponds to excitations at about 400 nanometers. So the question is, well, what's that all about? Okay, and it turns out that a way to think about it is in terms of the excitation of the conduction electrons in gold. So unlike a molecule where you tend to think of excitations involving exciting from an occupied to an unoccupied orbital, in this case, it's all the conduction electrons of the gold that end up oscillating coherently with respect to when you apply the light, the oscillating field of the electromagnetic wave. Okay, and there's some characteristic frequency of these oscillations, which corresponds to the 520 nanometers in gold and the 400 nanometers in silver. It turns out that this concept of plasma oscillations was something that was studied by Langmuir way back in 1929. He was not thinking about colloidal gold or colloidal silver. He was thinking about plasmas that occur in electric discharges. But it turns out the concept is kind of the same. Okay, and there's some characteristic frequency that he derived a formula for, which depends on the square root of the electron density, okay, in the plasma. In gaseous plasmas, that leads to characteristic frequencies in the gigahertz range. Okay, but it turns out then later, two theoreticians, Bohm and Pines, they wrote several very important papers in the 1950s related to the electronic structure of materials. And in one of those papers, they talked about metals, and they pointed out that that there's this characteristic plasma frequency that you could derive from Langmuir's formula. It's just the electron density is a heck of a lot higher. Okay, and so this leads to frequencies in the visible region of the spectrum, even in the UV for many materials. The only difference, though, is that this was for the bulk plasma, the oscillation in the bulk. But actually, if you have colloidal particles, then it turns out then you have the boundary conditions associated with the oscillations that occur in say, a sphere, and that leads to a surface plasma frequency that is the bulk plasma divided by the square root of 3 for the case of a spherical particle. But actually, you can get other numbers depending on the particle shape, the size of the particles, and also if you have many particles, the arrangement of the particles. And so it's really quite a diverse field. Okay, so just as an example of this, here I'm showing you some spectra that were these are distinction spectra associated with triangles of silver on a surface. This is work that came out of Van Dyne's group a long time ago. And they can make the triangles with different edge lengths and different thicknesses. And it turns out when they do that, you can tune this plasma, in this case, from 400 nanometers, okay, into the near infrared region of the spectrum. And actually, you can go even further than that for silver. And so this is just telling you, yes, these are really unusual optical effects because basically the color of the material depends on all these structural parameters associated with it. So that it turns out you can describe those properties pretty well with classical electrodynamics. Just put in the dielectric function, run a code that can calculate the optical spectra associated with classical electrodynamics, and you can describe these properties pretty nicely. Although in 2000, when Van Dyne did that work, that was something where we could just barely do the calculations. But now it's really quite straightforward. So that's fine. But then another thing that happened in the Van Dyne group, actually even much earlier, although the connections were not obvious when it was originally done, is surface enhanced Raman spectroscopy. So in this case, what you're doing is taking the same sort of, silver particles, let's say, and you're putting molecules on those particles, a monolayer of, say, pyridine. It turns out when they did that measurement, they've got this Raman spectrum. And of course, that's actually pretty similar, it turns out, to the spectrum of just pyridine in solution at high concentration. So in some respects, that's all fine. Okay, but it turns out that when you work out the intensity per molecule, you discover that this spectrum is enhanced by a factor of 1,000,000 compared to this spectrum. So then the question came up, why is that the case? And, a theory that was actually developed very early on in the business that describes quite a bit of it is to do classical electrodynamics. Okay, just simply ask the question, I've got an oscillating electric field. what happens that interacts with with the silver particle. It induces an oscillating dipole moment of the particle. There's a field associated with that oscillating dipole, and that can be enhanced actually. And so the molecules on the surface of the particle see this enhanced field compared to not having the particle. And it turns out there's a theory that says that this should go kind of like the fourth power of the field. So it only takes, say, a factor of 10 enhancement of the field to get a factor of 10 to the fourth enhancement of the Raman intensity. Okay, and so that's really quite a remarkable result. And you can describe that part of it nicely in terms of classical electrodynamics. But something that was realized actually even in the Van Dyne paper from long ago is that if you put different molecules on the same particles, you don't get the same enhancement effects. There's a chemical contribution to the enhancement, and that was something that you can't get out of classical electrodynamics. And so then the question is, well, how do you describe that? So something that we realized a long time ago, but could only do recently, is that you can develop an electronic structure theory of these plasmonic effects. Okay, and it just depends on these formulas. Okay, the induced dipole that I just mentioned is the polarizability of the particle times the applied field. Okay, and then if you have this polarizability, frequency-dependent polarizability, then you can calculate the extinction spectra of metal particles, and you can calculate the Raman intensity of molecules on these metal particles by just calculating these properties right here. So all you need then is an electronic structure method that can calculate these polarizability and derivative. Okay, and it turns out by the early 2000s that was possible using time-dependent density functional theory. So in work that I did with a former postdoc, Boston Jensen, back in the early 2000s, we developed the methods. Actually, it's well known but not implemented. And so for doing these calculations, okay, and then from this, we could calculate these optical properties with quantum mechanics rather than using classical electrodynamics. Okay, so we've done that. This is where we did an 84 atom cluster, soon to be tetrahedral, but that doesn't matter. It's just for convenience. For a silver cluster, and you get a peak at about 3.1 eV. That's the 400 nanometers that I was mentioning before. So, and if you dig into this plasmon peak, okay, you discover there's many electronic transitions underneath it. And if you dig into any one of those electronic transitions, you discover that they correspond to a coherent superposition of excitations from occupied to unoccupied orbitals or particle hole excitations. Okay, and so that's just exactly the sort of picture of what we would think of as a plasmon excitation for these particles. Okay, so that was a cool result. And later, another postdoc, Christine Akins, did calculations for different sizes of these particles of silver. Okay, and it turns out what we found was that you just get sort of the same result over and over again. Even a 20 atom cluster of silver gives reasonable behavior that you could think of as being plasmonic. Okay, and then what we see is that going to 120 atoms, it's really the same kind of result. It's just that there was a redshift, okay, in the spectrum when you do this. And in fact, if you do a lot of different clusters and you plot the plasma energy as a function of inverse size, you discover that it's qualitatively a straight line. And not only that, it allows you to extrapolate all the way to the large particle limit. Okay, and so this is now the limit where you think the classical electrodynamics should work. Okay, at say a frequency of 2.5 eV. Okay, and it turns out we did calculations using classical electrodynamics for the same structure, and we found that indeed you get this 2.5 eV. So this is then the connection then between the top-down theory and the bottom-up theory. Okay, there is a redshift as you go to particle sizes, but by the time you get to 20 nanometers, that part of it is over with. In fact, even 10 nanometers is way large enough for the redshift that comes from quantum size effects to be saturated. And so in the end, but that means that you can use these quantum calculations to calculate the smaller clusters and then infer from that what it is that might happen for much larger particles. And so then we said, okay, well, why can't we do this with for surface dense Raman? And so we did calculations for the pyridine onto a very small silver cluster, 20 atoms. Okay, and what we found was this is first the spectrum of just pyridine with no cluster present, and then with the cluster, you get a similar looking spectrum, but the intensity is dramatically higher. Okay, in fact, in this case, it was a 10 to the 5th factor higher. And so indeed that you would then say, oh, this must be the surface enhanced Raman effect. Okay, the spectra we got out of this look fortunately like what we calculated or what was measured in the experiments that I showed you. And so so yes, indeed, this seemed like you can get surface enhanced Raman into these really small little clusters. And fortunately for us, later, Martin Moskowitz did the measurements of, in this case, carbon monoxide onto 30 or 50 atom silver clusters, and indeed was able to observe a spectrum. The measurements were under conditions where there was also solid carbon monoxide present, so, but it's not near silver, so you can also get a Raman peak that comes from just the unenhanced spectrum. And it turns out that that overall you can estimate an enhancement factor. And he made estimates in the thousands range, but the wavelengths he was studying were not at the plasmon peak, so he would necessarily get smaller enhancements out of this, but nevertheless, he got a spectrum. Okay, and it shows that indeed you can get this out of very small silver clusters. All right, and there have been many other applications of this idea that using electronic structure theory since then. Okay, and also using density functional theory was really hard. So we gradually got interested in the idea of using semi-empirical theories like Indo, okay, for these calculations. So in work that I did with Rekha King, we collaborated with R. Karian. He was doing what were called tip-enhanced Raman measurements, okay, where you have a molecule that's attached between a tip, like in this case, a silver tip, and say a gold substrate, and you apply a potential. Okay, so we did a model of that where here's our tip, and then CO is attached to that. And in the measurements, they were able to show how the vibrational frequency of the CO can be modulated by the potential that you apply to this. Usually these days, we would call this a Stark tuning. Okay, but the reality is that there's chemical contributions to this as well because the CO molecules are covalently interacting with silver. But in any event, you get a certain result. And then we did the calculations using the same theories. And we found that indeed we get the same kind of Stark tuning that arises in this case. We didn't quite get the same slope of the curve, but qualitatively it's a similar thing. And so, basically, yes, you can get these effects that arise because of using electronic structure calculations. All right, so then, okay, we were interested in using semi-empirical methods like Indo for these calculations, okay, but it turns out that subsequently there's another code called DFTB it's the same idea, tight binding based code, and this got to be much more sophisticated starting around 2020, okay, where you could do now these real-time types of calculations. So this is where instead of solving just the standard electronic structure theory, you're instead propagating the Liouville equation, and you have a Hamiltonian that includes the coupling of the applied field to the dipoles in the molecule in it. So you get then the absorption and properties of this. You also can put in 98 Banach effects as well, but that's not important in this talk. And then you can couple that to the Ehrenfest approximation to look at motion of nuclei at the same time. So this is really a great opportunity to do things with this method. Okay, so we've done this. Okay, here I'm showing you using this method. This spectra again of a silver. In this case, it's octahedral particle going all the way up to 891 atoms, and you see the same result that I was talking about before with a redshift. Okay. And of course, an increase in intensity as you go to larger and larger particles. This sort of calculation is done by just calculating the time dependence of the dipole moment in the system using this Liouville equation approach, and then taking the Fourier transform, converting that into a polarizability, and then from this you can derive the cross section for absorption is what I'm applying here. So in this case, this is all pretty straightforward, and you can get a lot of other optical properties out of it. So here I'm showing you where we took the polarizability, calculated polarizability derivatives, calculated the Raman spectrum, and so this is then the surface enhanced Raman effect that we did in this case for pyridine interacting with a gold cluster. And now the cluster has 120 atoms in it, so a much larger thing than we could do previously, and we can go up to hundreds of atoms. This was actually important because for gold, it's hard to get plasmonic excitation until you get to hundreds of atoms. Okay, and so in this case, I'm showing you the spectrum associated with the gold cluster, and what we find is that indeed you see a peak at about 520 atoms. It's not 20 nanometers. It's not as strong as it would be if we went to larger clusters, but it's the same idea. And so from this, we can then calculate the Raman enhancement effect, and we can do it either tuning the frequency so there's no plasmon excitation, in which case you get enhancement factors that are on the order of a factor of 10. So that's the chemical effect. And then with if you excite at the plasmon for the gold cluster, then you get enhancement factors that are more in the range of what we did previously with the silver cluster. So yes, indeed, we can do a lot of interesting things with spectroscopy with this technology. All right, so then what I want to do is turn to talk about plasma enhanced photocatalysis, okay, because that's another thing that comes out of this capability that's really quite interesting. Okay, so photocatalysis means that you, in this case, you excite plasmons in these metal particles, and then that leads to an electron or a hole being transferred out of the particle and ultimately producing chemical reactions. So there's some work that we did with Chad Merkin way back 2001, okay, in which we did this and studied the growth of silver triangular prisms. Okay, actually they start out looking like this. It's a bit of a mess, but if you irradiate the system with room lights, okay, you can convert this mess into triangular prisms. And not only that, you discover that the size of the triangular prisms depends on the wavelength of the light that you use when you irradiate. So this is really a remarkable phenomena that where the photocatalysis dictates the size of the triangles. All right, so I won't go into the details on this, but overall it involves, again, exciting the particles. That leads to electrons coming out of the particles, reducing silver ions that are still in solution, and that leads to the growth of the particles. And so it's really a remarkable example of this effect. All right, but there's many other examples of plasma enhanced photocatalysis since then, and one that we got interested in was work from the Elanghalisis group, in which they showed that if you have gold particles in solution, and this is you're bubbling H2 and D2 through the solution, then it turns out when you turn on the light at 520 nanometers, okay, suddenly instead of having H2 and D2 coming through, you get HD coming out of it. Okay, so this is an example then where you're dissociating the hydrogen molecule as a result of this. They said it was impossible, but actually it turns out it's not very hard to do. So we got interested in this thing. So this was another postdoc, Yu Zhang, that was involved in this stuff. And he was working with some folks at Los Alamos, New Mexico, at the same time. And it turns out that the idea was to say, well, can we do this in real time? Can we hit this? This was density functional theory in real time, hit a gold cluster, and then an electron should come out, and does it dissociate? Okay. And so indeed that works. And this is just showing you that if you look at the HH bond distance as a function of time, these are just femtosecond type pulses. You found that if there's no gold particle, then it just oscillates. But if there is a gold particle, then it can dissociate. Okay, and not only this calculation also gives you some understanding of the electronic structure that's involved, because it turns out H2 has antibonding states that you can hit when you excite the system, and so that is what's involved in dissociation. So I won't go into more details on that, but then after that, we said, oh, now we can do this with this DFTB method. Okay, let's see what happens. And so we did it, and this is just showing you trajectories out of a calc simulation that we did. But this does require very high intensities to do. In fact, if you just use these little tiny particles, okay, then this ends up leading to intensities of 10 to the 13th watts per square centimeter. It turns out as you make the particle bigger, then the intensities go down and down. Nowadays with DFTB, we can go up to around 5 nanometers or so with this. Okay, that's still a ways off from where the experiments are, but even then, we still have these very high enhancement intensities that are needed. Okay, and so in the end, this is a problem for this this method, although we think that actually what happens is you never have a single gold particle. You always have particles that are collectively oscillating, and that we see even higher enhancements by another factor of about 100 or so. And so in the end, I think we can imagine that this could scale down to 10 to the 9th. And that's actually similar to the experiments that have been done with pulse excitation for inducing plasmon enhanced chemistry. So I think we're in the right ballpark on this, but it still is an issue. And here I'm showing you just the oscillations, the electron density that arise when you excite, in this case, the gold rod from this. But this gives you some insights as to what happens then when you look at dissociating molecules, water, CO2, and things like that. And what we find is that the water is dissociated primarily with hole transfer, okay, and then the CO2 is more of an electron transfer process. Okay, so that gives you some insights, and we then use that insight to explain an experiment that came from Prashant Jain. Prashant Jain is a faculty member at Illinois, and he did some very interesting experiments where he was doing both electrochemistry to associate water and CO2, and also doing it with plasmonic, turning on the lights basically. And what he found was that this is such that in the absence of the light, then it turns out that dissociation of CO2 to CO is pretty straightforward, but not water into hydrogen. Okay, but in the presence of light, then you produce a lot more hydrogen, okay, than CO2. So CO. And so in the end, that's kind of a story, but it came out of our calculations. We did both the static version by applying a field, and then we did it with this oscillating field from the plasmonic excitation, and it leads the same way. That it's easier to dissociate water with holes than CO2 with electrons, and so that's why that explains this experiment. Okay, so I'm just going to quit by saying we've also done this with aluminum, okay, which is also a nice plasmonic metal, except that the plasma energy is now at like 5 electron volts. But if you take octahedral shaped particles, then you get that. But if you do cubes, then it turns out you go to a big enough cube and you start seeing the effects of the electronic band structure of the aluminum showing up in the optical absorption spectrum. So that's which is a well-known aluminum feature at about 1.5 eV that shows up when we see it. So that's interesting. And then we've also dissociated hydrogen. It works very much analogous to what we've already talked about. All right, so overall, then we've found that we can replace then classical electrodynamics calculations with DFTB calculations, and this gives us a pretty good picture for understanding spectra. And then in addition, we can use that to describe this plasma-induced photocatalysis. And so there's actually quite a few applications now that we and others have gotten involved in recently, where we're starting really to get into what I would call the real chemistry part of this problem. And so this is really very exciting. Okay, so yeah, I mean, thanks. I've had lots and lots of people work on this stuff over many years. I couldn't list everybody, but these are the ones that kind of showed up in the talk. And then and then in addition, there's several people in my group that are currently working in this area. And then let me acknowledge, Rick Van Dyne in the very beginning, Chad Merkin, Terry Odom, and most recently, Prashant Jain for this work. Thank you very much.
Great. Fantastic talk. Thanks, George. All right, we are now in the question and answers. So if you have a question, please raise your hand, or if it's in the chat, you're welcome to. Go ahead and ask questions. Yes, R.A. Rosenstein, please go ahead.
Oh, George, thank you for a wonderful talk. I wonder to what extent, how does this notion of the polar return, does that possibly come into play in these studies? And how does the plasmonic description go over to the polar return description?
Yeah, I'll call it polaritons. So that's where, of course, anytime you have light that interacts with something, an excitation, you can start forming polaritons. The ones I was talking about today for these nanoparticles, the polaritonic effects are not all that important, but they still are there. Okay, but you can make polaritons and plasmons, or you can make plasmons and light interact to form polaritons in a whole bunch of different ways that are really quite exciting. Okay, and so yeah, so you take these same small particles, but you put them into a an array that shows Bragg diffraction effects. Then you can make these protons that are very you can mix the combination of how much of this is plasmons and how much is light. You can mix that over really quite a range. Is really quite an exciting field. And also people have done protons in a number of other types of applications with plasmons. And so, yeah, so I think that's an area where there's going to be this future research in which somehow that gets coupled into some of these chemical reactions that I was talking about. And it'd be nice to see where that's going to go.
Perfect. All right. Any other questions? All right, Oliver, please.
Yeah, thanks. Thanks very much for the beautiful presentation. I picked up one sentence. I believe I got this right. You said that for gold, it's hard to get plasmonic excitations unless you're going to hundreds of atoms. Did I catch this correctly? And I wonder, given the topic of your talk, if you could maybe just say a few more words about this transition between, the microscopic picture of single excitations to this collective excitation of a plasmon. That would be great.
Yeah, it's a great topic. As you go from small, like just a few atoms clusters, then you're in the, more the molecular regime, and then you go to larger clusters, then eventually the excitations become plasmonic. And I think I mentioned for silver, you start seeing things that start looking very much plasmonic by the time you get to about 20 atoms or so, and that's really neat. But gold has these, the d orbitals are accessible at wavelengths that are basically where the plasmons are, and so in the end, it turns out you don't get the nice plasmonic behavior for you to go to small clusters like 20 atom clusters, and so so that's a real problem. So people got interested in that question. There was always this thing about when do you really see nice plasmonic behavior for gold? Okay, and actually, fortunately, there were people like Ron Chargin who could actually make clusters with different sizes, and eventually the verdict came out as being something like, well, maybe 250, maybe 300 atoms. Okay, it actually depends on what property you look at, exactly how that works. Okay, but yeah, so that's the problem. That was actually one of our challenges, why we needed to go to these larger clusters that we need to use DFTB, is that we wanted to study gold and we couldn't for the longest time. Okay, but with DFTB, we can finally do this with hundreds of atoms, and so that really makes it all feasible. Yep.
Great, thanks very much.
All right, wonderful. Well, to be on time here, let's join me in thanking both of our speakers today, both Camille and George, for wonderful talks. And to see next time, we have Dr. Tian Q from Princeton University and Professor Kongkwan Ni. So please join us again on October 10th. Wonderful. Thank you, everybody.
Thank you.
Thank you.
Thanks, everyone.